KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
Students, now in this video, so we are going to discuss
in continuation to the last class. This is 6th class from starting of this chapter, which is rotational motion 6. Okay, right. In this class, we are going to discuss angular velocity and its relation with linear velocity. You know, angular velocity and its relation with linear velocity. Okay, its relation with linear velocity, right? If you observe carefully here, we are going to study in this class, we are going to study the relation between angular velocity and linear velocity. Angular velocity and linear velocity, right? So in this class, you know, this is what board point of view, right? Very clearly we are going to focus on angular velocity with respect to linear velocity. Generally, linear velocity means once we need to go back to that is what motion in a straight line. Okay, but there we consider whole body as a single particle. But generally, linear velocity means whenever linear velocity applied on a body or on a particle of certain mass, then the body is going to get, that is what a translatory motion, that is what motion in a straight line, and there itself that is what linear velocity is the rate of change of displacement. This is all in case of motion in a straight line when we assume whole body as a single particle, right? And you apply only linear velocity on that body, but that is not our discussion now. Our discussion is, we are in the chapter of rotational motion. That is what you know, a body is in rotational motion, right? So from our previous classes, we learned what is rotational motion and what is the difference between rotational motion and circular motion. At the same time, what is a rigid body and what is a non-rigid body. These are all we discussed, right? So now we are going to see the two things, that is what the angular velocity and angular acceleration also. But initially our focus is to study the relation between angular velocity and linear velocity. So when we are going to study the relation between these two, we have to focus what is angular velocity. And then you can see the relation between angular velocity and linear velocity, right? Okay. So see here, what is the angular velocity and its role in rotational motion? That is important thing. I'll repeat once again. What is the angular velocity and role of angular velocity in rotational motion? First you have to concentrate. Okay, right. You know, we have seen that every particle of a rotating body moves in a circle. In case of rotational motion, every particle on the body, every particle of rotating body moves in a circle. You know, the linear velocity of the particle is related to the angular velocity. That's we know, because already from lower classes onwards, you know, that is what length of the arc is equal to radius into angle. Similarly, velocity is equal to radius into angular velocity. Linear velocity is equal to radius vector into angular velocity. Therimo, right? From lower class onwards, therimo. But here 4 things: rigid body, rotational motion, circular motion, involvement of angular velocity, and relation between linear velocity and angular velocity. That is the topic completely. Okay, right. See this. The relation between these two quantities, that is what linear velocity and angular velocity, now we are going to see. See here. You see this picture. In this picture, this is what rotation about a fixed axis. This is the fixed axis, and it is the rotation about a fixed axis, right? So first, particle P of the rigid body, particle P of the rigid body rotating about the fixed axis, that is what the z axis, right? And here the particle P moves in a circle of radius. This is the radius now. And C is the center on the axis. So this is the axis of rotation, and you have to imagine a rigid body here. On that rigid body, P is one of the particle. In certain time interval, that is what delta t, the particle moves from here to here. Okay, that now we will see now. So first I am explaining the picture, that is what the figure, right? It is x axis, y axis and z axis. It is the direction of linear velocity. Direction of linear velocity. Okay, right. See this. In rotational motion of a rigid body about a fixed axis, every particle of the body moves in a circle which lies in a plane perpendicular to the axis. Okay, right. I will repeat once again. It's an important point, right? In if it is possible, you keep in mind. In rotational motion of a rigid body about a fixed axis, every particle of the body moves in a circle which lies in a plane perpendicular to the axis. So which lies in a plane perpendicular to the axis? The particle, this is what, see here, right? Circle which lies in a plane perpendicular to the axis. This is the axis, so the circle is perpendicular to this, right? Okay. The following figure, right, shows a typical particle at a point P, right, of the rigid body rotating about a fixed axis. This is the fixed axis taken as z axis, right? The particle describes a circle. The particle describes a circle with a center C on the axis, right? Full stop. The radius of the circle is r. Okay, right. So this is what r. Okay, right. Next, it is the perpendicular distance of the point P from the axis, right? So what is radius? Which is the perpendicular distance of the point P from the axis, right? This angle is also, you can assume as delta theta. This angle, the angle from P to B dash, you can assume as delta theta, right? And it is what perpendicular vector, that is what perpendicular distance, that is what r bar, right? We also show that linear velocity v of the particle at P, right? This is the linear velocity v of the particle at P, right? It is along the tangent at P to the circle, right? Next, let P dash be the position of the particle. Let P dash be the position of the particle after an interval of time. Delta t, right? So generally the particle, when a body is in rotational motion, the position of each particle is changing, right? So here P dash is the position of the particle after certain interval of time, that is what delta t. Right, the angle PC P dash, this is what delta theta. It is what delta, angle P dash. It is what the angular displacement delta theta of the particle in time delta t. Okay, right. Now the average angular velocity of the particle. Here, the average angular velocity of the particle over the interval delta t is delta theta by delta t. Delta theta by delta t. You know, that is what generally linear velocity means what, ma? So linear displacement by time. Similarly here angular velocity means what? Angular displacement by time. That is what? Delta theta by delta t. You know, as delta t tends to 0, you just imagine, we have to imagine. Here delta t, as delta t tends to 0, that is takes smaller and smaller values, smaller and smaller values. You can imagine, ma, see here. So the body is rotating, you know, as time is more, what will happen? You can expect more angular velocity, no, in magnitude I am talking. In magnitude, you can expect more angular velocity, no. And there is a difference between linear displacement and angular displacement. You know, in case of angular displacement, the path is fixed. You know, the angle increases like from 0 to 90, then to 180, then 270, then 360, then again to 720, like that. Okay. But in case of linear displacement, not like that, no. The path is not fixed. For example, 1 by 2 kilometer, I mean half kilometer, 1 kilometer, 2 kilometers, 3 kilometers, like that it is going to increase, right? That is what the ratio delta theta by delta t approaches a limit, which is the instantaneous angular velocity. That in symbol, it is what? Omega. So here also it is there, not only here, right? Just simply I have written there. It is what? A symbol omega we are using to represent angular velocity. Anyhow, as delta t tends to 0, that is what? Taking smaller and smaller values, the ratio delta theta by delta t approaches a limit, which is the instantaneous angular velocity d theta by dt of the particle at the position P. Okay, right. You know, delta theta means somewhat a big difference. For example, delta theta means, how can I say? Okay, right, I will tell you. Delta theta means a big change in theta. D theta means a small change in theta. That is the difference between delta and D. Delta and D. Except that remaining is same. That is what? Here also angular displacement. Here it is the time interval. Here also angular displacement. Here it is the time interval. Even time interval also, here we are taking large time interval. Here we are taking small time interval. That is the difference between this one and this one. Okay, right. See here, angular velocity of the particle at the position P. At the position P. Okay, right. And you know, here I already told you, that is what? Omega is the notation. Omega is the symbol to represent angular velocity. To represent angular velocity. Okay, right. And you know, from our previous studies, that is what? From our previous study of circular motion, that the magnitude of linear velocity v of a particle moving in a circle is related to the angular velocity of the particle omega by the simple relation v is equal to r omega. V is equal to r omega, and r is the radius of the circle. R is the radius of the circle, right? So this is what I already told you while starting of this class. That is what, you know, in mathematics also, geometrical mathematics, in case of circles topic, so we got that length of the arc is equal to radius into angle, right? Angle you should take in radians, right? So whatever it may be the unit, but generally you know that in mathematics length of the arc is equal to radius into angle. Radius into angle, right? So from that, you know, if you differentiate on both the sides, that is what? Okay, if you differentiate on both the sides, you know, it is what? dl by dt is equal to r into d theta by dt. You know, dl by dt means it is what? Displacement by time means velocity on one side, that is what? Linear velocity. And on the right hand side, you know, r is same because it is a constant, and then d theta by dt means omega. So from L is equal to r into theta, mathematically also you can get it as v is equal to r omega. V is equal to r omega, right? Next, see this. In case of all particles of the body, in case of all particles of the body, it is what you can write Vi is equal to R, because it is the general thing, right? Because in one rigid body means not only one particle, no. So for every particle you can apply the same thing. That is what I is equal to 1 to n. I is equal to 1 to n for all particles. In case of all particles of the body, Vi is equal to R into omega I is equal to 1 to n. I is equal to 1 to n. Okay, right. And in the bracket he has written what is the I value which changes which changes from 1 to n to satisfy all the particles of a rigid body. Okay, right. And here, for example, you just assume R is equal to 0. Then what happens to the V? 0 only, no? When R is equal to 0, mathematically, I am asking you to imagine mathematically. So, R is equal to 0 means, when R is equal to 0, ma? Right? Suppose it is the perpendicular axis, just now I showed you one picture, right? So, when the perpendicular distance from axis of rotation to a particle position is 0, then what about its linear velocity? 0 only, no? Right? So, when the linear velocity is 0, what does it mean? Right? When linear velocity is 0, what does it mean? When linear velocity is 0, automatically the particle is said to be at rest, no? The particle is said to be at rest. Okay. So, what can we say? Particle on the axis are stationary, because when the particles on the axis means R is equal to 0, V is equal to 0, then you can say that the particles on the axis are stationary, right? So, this verifies that the axis is fixed. The rotational axis or the axis of rotation is fixed. Okay, right. And you can also say like this, ma. So, this is what whatever we have angular velocity, it satisfies, and it is like angular velocity of the whole body when R is fixed. When R is fixed, omega is the angular velocity of the whole body. And you can also say that, see here, pure translational of your body by all parts of the body having the same velocity at any instant of time. Similarly, we may characterize pure rotation by all parts of the body having the same angular velocity at any instant of time. At any instant of time, right? So, based on this, I will repeat once again, here he is comparing pure translational and pure rotational motion, right? In pure translational, we know, that is what in the chapter of motion in a straight line we discussed, all parts of the body having the same velocity at any instant of time. Similarly, in case of pure rotational motion, all parts of the body having the same angular velocity at any instant of time. Okay, right. And based on this, you can also say that each part of the body moves in a circle which lies in a plane perpendicular to the axis and has the center on the axis. See here, each particle of the body moves in a circle which lies in a plane perpendicular to the axis and has the center on the axis. Next, the magnitude of the angular velocity. Okay, that is what. Before going to see this, we want to talk about the angular velocity. Angular velocity is a vector still now, but from this topic onwards, we are considering it as a vector because of having magnitude also in rotational motion point of view, right? Okay. And one more thing is, for rotational motion about a fixed axis, the angular velocity vector lies along the axis of rotation, and points out in the direction in which a right-handed screw would advance. If the head of the screw is rotated with the body. And you can also see here, see the two pictures. See, if your body is rotating like this, what is the direction of the angular velocity? This is. If your body is rotating like this, what is the direction of the angular velocity? Like this. And magnitude of the angular velocity vector is omega is equal to d theta by dt. Okay, that is what, right. Next, this one, which is what here, angular velocity vector omega is directed along the fixed axis as shown. Angular velocity vector omega is directed along the fixed axis as shown. This is the direction of angular velocity, right? And the linear velocity of the particle at P that is V is equal to omega r, and it is perpendicular to both omega and r and is directed along the tangent to the circle described by the particle. It is also same like yesterday we discussed, vector product, right? That is what omega bar cross r bar is equal to omega cross OP bar, and this OP, this is what okay, it is what OP. This OP means you can write that is what OC plus CP, right? So then, but omega cross OC bar is equal to, that is what 0 bar, because there is no R, and omega is along OC. And one more thing is omega cross R bar is equal to omega cross CP, that is what from here to here, right? Afterwards, after completion of this, you come to this point, that is what omega cross CP, the vector omega cross CP is perpendicular to omega, that is to the z axis, okay? See here, see the continuation here, that is what the vector omega cross CP is perpendicular to omega, that is to the z axis, and also to CP, right? The radius of the circle described by the particle at P, and also to CP, the radius of the circle. So what is CP he is saying? That is the radius of the circle described by the particle at P, right? It is therefore along the tangent to the circle at P. It is tangent to the circle at P, right? And afterwards, if you observe carefully here, that is the magnitude of omega cross CP. The magnitude of omega cross CP, and omega and CP also perpendicular to each other, right? And if you see this omega bar cross r bar, that is what omega cross r is a vector of magnitude, that is what omega into r perpendicular, that is what omega into CP, omega into r perpendicular. And here, right, and here if you observe carefully, that is what is a vector of magnitude omega r perpendicular, and is along the tangent to the circle, described by the particle at P, right? The linear velocity vector V at P has the same magnitude and direction. Thus, V is equal to omega bar, that is what omega cross r, right? So what he is saying here is, omega cross r perpendicular has the same direction of the linear velocity. Linear velocity also having the same direction. Then what can we say? V is equal to omega cross r. V is equal to omega cross r, right? So this relation holds good even for rotation of a rigid body with one point fixed, such as rotation of the top. Similarly, in this case, the r represents the position vector of the particle with respect to the fixed point taken as together, okay? So like that he proved V is equal to omega cross r, that is the relation between linear velocity and angular velocity, right? At last we want to say some information, that is what, see here, for rotation about a fixed axis, the direction of the vector omega, for rotation about a fixed axis, the direction of the vector omega does not change with time. For rotation about a fixed axis, the direction of the vector omega does not change with time. Its magnitude may, however, change from instant to instant. Its magnitude may change, and the change is from instant to instant. And for the more general rotation, both the magnitude and the direction of omega may change from instant to instant, okay? That is what he is talking about, angular velocity, okay, right? Next, angular acceleration. If you know that linear velocity, how can we find, if you know linear displacement, how can we find linear velocity? Similarly, now we got angular velocity. You know, angular acceleration is the rate of change of angular velocity as a scalar quantity, right? In this, that is what, as a scalar quantity, as simple as such, angular acceleration is the rate of change of angular velocity. That is what alpha is equal to d omega by dt, d omega by dt, right? So here also, in a similar manner, that is what you can define in rotational motion. It is the concept of angular acceleration. It is similar like linear acceleration. In linear acceleration means that is time rate of change of velocity, no? So in rotational motion, time rate of change of angular velocity is simply called as angular acceleration. See here, right? So time rate of change of angular velocity. If the axis of rotation is fixed, the direction of omega and hence that of alpha is fixed, in this case the vector equation reduces to a scalar equation. Same thing, that is what alpha is equal to d omega by dt. Okay, right. So in this class we concentrated to discuss the rotational motion of a rigid body in terms of angular velocity. At the same time, we also discussed about angular velocity, whether it is scalar or vector, right? And what about the direction of angular velocity? And then we went to discuss the relation between angular velocity and linear velocity, that is v is equal to omega cross r. At last, we discussed what is angular acceleration. Okay, right. So in our next class, we will continue with next continuation topic. Thank you.